Good morning. It's a beautiful sunny morning coming from Churchville, New York, and it's a perfect day for you to sit inside in your warm houses and learn some calculus. So here we go. All right. So yesterday we were talking about some washers going around some weird axes of rotation. So I'm going to start with a couple more of those. And then after that, we are going to get right into the last method of volumes, which is the shell method. So here we go. This is I believe day 91. And more washers. And intro to shell method. All right. So from last class to start out with, near the end of class, I was giving you lots of different axes to rotate this one region around. So let's start with a couple more of those. That region we were talking about yesterday was the region bounded by y equals x squared and y equals radical x. We're going to find the volume. When it's revolved about so I'm going to break off. We'll start with y equals -2. Right. So I would need to draw this out, and I know we did it yesterday, so I'll do it kind of quick here. But we had y equals x squared, looking something like that, and y equals radical x, looking something like that. So that's x squared, that's radical x. And we know the intersection points. We got one down here at 0, 0, and we also have one up here at 1, 1. And that's my region. Okay, so now the axis I'm going to revolve around is down here, y equals -2. So when I revolve that region around there, we'll have a little bit of a gap, because obviously there's a gap between that and the axis that we're going around. And if you kind of think of what the reflection would look like, we'd want our rectangle perpendicular to that axis of rotation. So is it going to be dx or dy? It's going to be dx, so we're in terms of x, so that's good. And you can see that I've got a washer because there's that middle section that's missing. Okay, so we're ready to set up the volume equation. What always comes out front? Pi times the integral from, or in terms of x's, but the x's and y's are the same for my intersection points, so definitely 0 to 1. All right, and take a second to think about it. What's your outer radius going to be? So my outer radius is going from the axis of rotation way out to here. So if it was just from the x-axis, this spot, what would your outer radius be? Radical x, but since I also have this far to go, it's going to be radical x plus 2. You can think of it as radical x minus -2 if you really want to. But essentially it's going to be radical x plus 2. We got to square that. Then we're going to subtract off our inner radius. So our inner radius would be going from our axis of rotation up to that lower curve, which is x squared. So what's your inner radius going to be? Hopefully you're saying x squared minus, or plus 2 minus negative 2 squared. Don't forget your dx at the end, because that's your height of your rectangles. Remember, it's pi r squared h minus pi inner r squared h. That's where it comes from. And the setup is the most important part, so now you can go type it into your calculator. I've only got an old calculator to work with today, so you have to bear with me. It's math 9. You have to put in parentheses, radical x, plus 2, parentheses squared, minus, parentheses, radical x. Oops, what am I doing? X squared, plus 2, all that squared, comma x, comma 0, comma 1. I know it's going to be a lot faster on your calculators. When I plug it in, I get, it's trying real hard, that number, which I don't know if that's going to math frac. Nope, so I'm just going to multiply it by pi, and I get, oops, I didn't actually do that. Let's see what I can do here. I want that one, I want that one, I want that one. We're going to multiply it by pi. Times pi. And we get 5.131. Okay. Questions on that one? Hopefully not. All right, last one like this, and then we'll get into this new shell method. So it's the same region, that radical x and x squared, but for the last one here, I want to rotate around y equals 5. Okay, so let me draw this out. And I'm going to need to go up this time, so I'm going to kind of make it a little bit lower. There's y equals x squared. There's y equals radical x. Label those. That's x squared, radical x. And let's say y equals 5 is up here. So I want to revolve around that. So if we picture me revolving it, we'd get a shape like that up here. Draw your rectangle. There's still going to be a dx rectangle because we're perpendicular to the axis of rotation there. And there's your inner radius, and there's your outer radius. So we still got a washer, obviously. And when I go to set this up, what's it going to look like? It's going to be pi times the integral from 0 to 1. Okay, let's think about our outer radius. We're going from here all the way to that line. What's it going to be? All right, so you got to be a little more careful with this one, because remember that if you said something like x squared minus 5, you got it a little bit backwards. Because remember, this down here, that's the x squared part. So really, I'd have to do the whole 5 distance minus the x squared part. And I want to square that. And the inner one is coming to here. So a similar idea there, we're going to subtract 5 minus radical x squared. And don't forget your dx on the end. All right, so we can plug that into the calculator. I'm assuming you can do that. And you should get an answer of 9.529. You might want to try that on your calculator, though, to make sure you're getting the right answers. It can be a little tricky with the squareds and things like that. All right. All right, so that was kind of the end of yesterday's stuff with the washer methods. And like I said, today we're going to get into something called shells. So I'm going to start a new piece of paper. If you've got room, you can just keep going on yours. But here we go with the shell method. All right, so some background, and then I'll kind of try to draw a picture to make a little more sense for you. The nice thing about the shell method is that the shell will be formed by revolving a representative rectangle that is parallel to the axis of rotation. Now that's kind of a big deal because I've been saying all along that your rectangle had to be perpendicular to your axis of rotation. So that kind of forced us into dx sometimes or forced us into dy other times. And as you saw in that one homework assignment, it's really annoying sometimes to make it in terms of the other variable. We had to do complete the square yesterday to get that dy rotation that we needed. So since now I have this extra option that I can always draw a rectangle parallel to the axis of rotation, this method will help us avoid having to change an equation in terms of another variable. And the nice thing is it works with whether the other method would have been a disk or a washer. So basically, if I know how to do the shell method, I never am going to have to rewrite my equations in terms of other variables. I can always keep it how it's written originally, if that's easier for me, and get the same answer. So this last bullet kind of puts it all together with the shell method. When we use the vertical axis of revolution, we'll keep all values in terms of x. So that's basically just like what I've been saying. A vertical axis of revolution means essentially we're going around the y-axis or some up and down line like that. And I don't have to do dy in that case anymore. Now I can do dx, which will make some of our questions a lot easier. Okay, so let me try to draw a picture to explain how this works and where the formula comes from. So let's consider a revolution about the y-axis. So here's a picture. And let's say this is my graph. And let's say I'm going to cut it off here. So this region, I'm going to revolve around the y-axis. So that means on the other side, it would look like this. Now, in the past, don't write this. If I was going around the y-axis, I always talk about having to do a rectangle perpendicular to that axis. So it would have to be a dy because this distance is a y distance up and down, so it's a change in y. I don't need to do that anymore. That sometimes caused us to have to rewrite equations using complete the square or whatever. So now I'm going to use a vertical rectangle. So now that's a left and right distance. That's a change in x anymore, or a dx. Okay, now if you can picture this, I'm revolving around the y-axis still, so it's hard to show you on a computer here, but if I take that rectangle between my two fingers, pull it out around the y-axis and go around, eventually it would end up over here. It would rotate around this way and then this way. And up top, it would rotate around this way and then this way. So what shape does it still kind of look like? It's still a cylinder. We call it a cylindrical shell. And if I take one of those little rectangles out of it, here's what it kind of looks like. So first off, this creates a cylindrical shell. Here's the height of my shell. So if I draw like one cross section of it, there's my height. As I rotate around, it creates the cylinder. And since that rectangle had some sort of width to it, your cylinder kind of has a little width to it as well. Something like that. You can kind of think of it like a soup can. There's a thick soup can, I guess, if you want to think of it that way. Or sometimes I picture it as like that shell that covers the outside stage at the Parrington Park next to the school. It's a shell that kind of goes around like that. So in this shell, if I wanted to find the volume of that shell, there's my radius. And on my picture over here, there's my radius. And this little thickness to it, this piece in here, would be delta x, because that's coming from that thickness from the rectangle there. So if the shell was cut open, what shape would you get? Well, if you picture me like cutting a soup can in half right here and stretching it out, you'd get a rectangular prism. So I could always like cut a cylinder down the middle, stretch it out, get a rectangle shape, but since there's also that little bit of thickness to it right there, that's what causes the rectangular prism to happen. So that leads us to this picture. So here's the soup can that's been cut open. But again, there's some little bit of thickness to it. That's our delta x, so it's going to be pretty small. You can see I have a rectangular prism now. And this is still going to be the height. And this is still going to be delta x. But what's this distance going to be? Well, it was originally the distance from here all around the soup can. What do we call that distance? Circumference. And what's the formula for circumference in terms of radius? 2 pi r. So the volume of that rectangular prism that we get is length times width times height. The length is 2 pi r. The width is delta x times the height. And that right there would represent the volume of one shell. But if I take all different rectangles all throughout this and rotated them around, we'd have lots of different shells that we'd have to add up. So putting that all together, the sum of all such shells in a region, and as the limit is that delta x goes to 0, gives us an integral. Now 2 pi is the constant this time, so that's going to be out front, times the integral from a to b, whatever our bounds are still, times the radius of the shell, times the height of the shell, times delta x, or dx. And that is a shell formula. And that's a shell formula using a vertical axis of revolution. Because everything's in terms of x. All right, so you'll notice in that formula there's no squareds like there were with disk and washer. And that's because disk and washers were taking the sum of disks or cylinders, pi r squared h. Rectangular prisms don't have any squareds in them, so that's why there's no squareds in the formula. So don't confuse that. And also know that there's got to be a 2 pi out front, because again, coming straight from that formula, the length of the rectangular prism is the circumference of that cylinder, so 2 pi r. Okay, last thing I'm going to say about this before we do some examples. If using a horizontal axis of revolution, like the x-axis or something like that, the shell method would use y-bounds. And we'd integrate with respect to y. Or dy. So as we kind of switch between this and what we've been doing the last few days, the thing to remember is when you draw your rectangle, now don't draw it in terms of what I'm rotating it around, draw it in terms of what you want your equation to be in terms of. So if I want to do dx, draw your rectangle up and down. If it's perpendicular, we'll use disk or washer, and if it's parallel to the axis we're going around, we'll use shell. And similarly, if you want your equation in terms of y, draw your rectangle going left to right, horizontally. And then if it's perpendicular to the axis we're going around, we'll use disk or washer. And if it's parallel, we'll use shell. But we'll never have to change the equation again. Okay, so let's do a couple examples. And then we'll be done. Okay, number 1. Region bounded by y equals x squared. And y equals 2x is revolved about the y-axis. Find the volume. All right. So as always, we're going to start by drawing a picture. This one's not too crazy of a picture to draw. So if you want to think about your intersections, we could set the equations equals. X squared equals 2x. I'm going to solve that. I'd have x squared minus 2x equals 0. Pull an x out, leaves us with x minus 2. So we're going to intersect at x equals 0 and x equals 2. All right, so I know I have to go over at least to x equals 2. So we've got 0, 0, 1, 1, 2, 4, and there's my x squared graph. And then for 2x, we've got 0, 0, 1, 2, 2, 4. Sorry, not my greatest picture that I've ever drawn here. And we're rotating around the y-axis. So when I rotate around, we're obviously going to get the reflection shape over here. But again, in the past, I would have told you if we're going around this way, I have to draw a dy rectangle. And that means I'd have to have everything in terms of y, so I'd have to change these two equations. I don't have to do this anymore. So since my equations are already in terms of x, when I look at this, I would say, okay, I want my rectangle to go up and down. So then when I rotate around, it's going to look something like that. And I have a shell. Okay, so now when I write the volume equation over here, what's going to go out front? Again, if it's a shell, 2 pi goes out front because coming from that circumference part of the equation. What would my bounds be? Well, my intersections are 0, 0, and 2, 4. But since my rectangle is a dx rectangle, we want to use the x coordinates, so 0 to 2. And if you look back at that formula I wrote a second ago, it was the 2 pi times the bounds from 0 to 2 times the radius of the shell. So now this is the part that always kind of didn't make sense to me right away. Here's the radius of the shell. What is that? Well, it depends on where you draw your rectangle. Here the radius is that distance, here it's that distance, here it's that distance. But it's whatever x distance we're talking about. All of these values are x values. So the radius of the shell is actually just going to be x here. And that's usually what it's going to be, or always what it's going to be if you're going from the y-axis. It's an x distance out. So I go out some x distance, that's my radius. The height of the shell is just this part of our rectangle. So what would that purple height be there? It's top minus bottom. So the top equation is 2x minus the bottom equation is x squared dx. I remember neither of these are squared because length times width times height, a rectangular prism's volume isn't squared. All right, so I think the purple part should make sense to most of you. That's the height. I get that the radius could be a little weird to think of. Like, I used to think it should be whatever this first equation was, and it is kind of, but it's in terms of, this would be a y distance from here to here. So it's a whatever x value we're using, however far x I'm going out. Okay, so plug that into our calculators, and if I do that, I'm going to do math 9. So it's the integral of x times 2x minus x squared comma x comma 0 comma 2. And I end up with that number, which should math frac, I would hope, 4/3. But then think about what you're doing. It's 2 pi times 4/3. So what's your final answer? 8 pi over 3. Or if you put the pi in there, it would come out to be 8.378. Either would be acceptable. All right, so I was able to find that region using a shell, and I didn't have to change my equations. But just as a side note, what if I wanted to use the washer? If I use the washer, then I'd have to have my rectangle going the other way. So same idea, right? There's my region. But now I need my rectangle going this way, because if you're using a washer, it's got to be perpendicular to your axis of rotation. There's my washer. And if I do that way, the volume would have been what out front? Pi times the integral from, what would your bounds be? You'd have to use your y bounds, 0 to 4 of the outer radius. So the outer radius is to the parabola, but I have to be in terms of y. So when I had y equals x squared, we need to rewrite that as x equals radical y. So my outer radius would have been radical y squared. And my inner radius would have been to that 2x equation. But instead of y equals 2x, I would have needed x equals y over 2. And now it's dy. Let's plug that in and see what we get. Math 8. Oops. Math 9, I mean. So radical y squared would just be y, or x, minus y over 2 squared. Oops, where'd that times get in there? Comma x, comma 0, comma 4. And it looks different, but that's just because there's only one pi out front. Still gets us to 8 pi over 3. So you get the exact same answer. And again, the advantage to using shell is we don't have to do this step where I have to worry about rewriting my equations. It wasn't too hard in this example, but remember that one from the homework? That was soup nast, so you wouldn't have wanted to do that. And by the way, let's go back to that question. So for my last example, this is homework 6-1, that worksheet. It was the first quadrant region. Bounded by y equals 2x minus x squared, and the x-axis revolved about the y-axis. Value. Okay, so again, this is literally the exact question that I talked about yesterday where we had to use complete the square with. It's from that worksheet 6-1, problem set 84, I think. And you saw yesterday, 2x minus x squared basically looks like that. This is 0, this is 2. And we're revolving about the y-axis. The x-axis was easy. That was just an easy disk. But yesterday when I did the y-axis, we had to do that weird complete the square thing to solve in terms of y, because I had to use a washer. Look at how much easier it is now. I can just do a rectangle going like that, a dx rectangle, that's parallel to my axis of rotation. So when I revolve it, I get this cylindrical shell. So my volume would be, it's a shell, so what goes out front? 2 pi times the integral from, we're using dx's, so we're using our x values, again, 0 to 2. What's the radius of the shell? Well, again, I'm going out any x value that I feel like. I can pick your favorite x value and you can find another rectangle. So the radius is going to be x. What's the height of all of these cylindrical shells? The height of the rectangles. It's just my equation, 2x minus x squared dx. Remember, no squareds because it's a rectangular prism, length times width times height. That's all it is. So I can just type math 9 x times 2x minus x squared comma x comma 0 comma 2. It's that same answer we got a second ago. I think that's 4/3, right? So it's 2 pi times 4/3, and there's your 8 pi over 3 again, which is the answer you should get on that worksheet if you do it with the washer, but it's a whole lot more difficult because you had to split it up into a top minus bottom with your plus or minus square roots. Really gross. And this is way faster. So moral of the story is use the shell method when you have to change your equations. Because if you can avoid changing your equations, your life is going to be a lot better. All right, that's all that I've got for you on this video. I am going to post the next problem set, which is another worksheet. Problem set 86, I think. It's worksheet 6.2. So I'll send that to you and post it on my website. If you want to start working on that, that'll be due next Friday. But you've got plenty to work on today. There's a take-home test due Tuesday. You've got homework due for this week. And you can always email me, and I will be happy to answer your questions today. Enjoy your day full of math.